Hello, this is a lecture on quantum physics for my Sem 4 student. I would like to re-emphasize on the fact that it is impossible to have a precise trajectory for a given particle of microscopic size, which is already proved by using the uncertainty principle and the Davison-Germer experiment. But I have another example which I have already drawn as a picture to clarify the concept of really having a mental picture in mind, to clarify that particular mental picture, how one can really have a representation of a quantum state by in terms of mathematical structure, in terms of, let's say, matrices. If we want to represent the quantum state of a system, then how can we really think of the situation? So let us consider a closed pipe as it is given over here. We have a closed pipe which contains a particle, and this pipe is of length L as is given in the picture below. And we can subdivide this closed pipe into a number of intervals, let's say n number of intervals, and we have a particle which can oscillate to and fro within this particular closed pipe, and the corresponding coordinate is given by xt as written over here, the xt. And now if we want to assign the particular position of the particle x as a function of time, then we can assign it in the classical mechanical way, or we can also have a representation of the dynamical state of the particle by a matrix like this. For example, if the particle is in the first interval, then we can represent it by a column vector, n-dimensional column vector, because we have n element or n intervals, and each interval have a length epsilon is equal to L by n. So if it is in the first interval, then we can define it by a column vector, n-dimensional vector 1, 0, 0. So there are n element within this n-dimensional vector, in which the first element is 1 because the particle is in the first interval. In the same fashion, we can define the particle, for the particle to be in the second interval, to be 0, 1, 0, 0, 0, and so on, n element again, but now the second element of the column vector would be 1 and all other elements would be 0. Similarly, for the particle in such a fashion to be in the nth interval, we can always write epsilon n, or a vector, n-dimensional column vector, as 0, 0, 0, and the last element would be 1. Okay. Now, what would the vector v, which is a epsilon 1 and b epsilon 2, represent? It is simply a column vector which have a as the first element and b as the second element. Now, if you try to think this in the classical mechanical way, a particle concept, that the particle cannot be simultaneously in the interval 1 and the interval 2, but if you can have a concept where you are thinking of the wave nature of the particle doesn't have a specified boundary, as it was observed in the Davison-Germer experiment. That is an experimental proof. The second one we studied was the double slit experiment, where an electron can interfere because you have a single source, and whenever you are opening two slits simultaneously, then you have regions of intensity in the screen where you have zero intensity, so the electron can never ever reach on those zero intensity regions. So if you want You can explain that by assuming the electron to be a wave which can simultaneously reach the two slits, or which can go as a wave, which can simultaneously go as a wave on both the slits simultaneously. If we assume the wave nature of the moving particle, then both the slits can be simultaneously illuminated or simultaneously visited by a single electron. So that is the case, that is the mathematical case here. If you have a two-level system or two-slit system, then you can always define a vector V is equal to AE1 plus BE2. And if you have a three-level system or three slits, then also you can write it as AE1 plus BE2 plus CE3 and so on. So a physical state, quantum mechanical physical state of the system can thus in this particular case be represented as a psi vector, which is equal to psi1 E1, where psi1 is actually representing the probability amplitude of the particle to remain in the state in the first interval, psi2 E2 plus dot 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 psi-n En. So that is how one can represent a particular state, quantum mechanical state of the system. Now, if we want to know the probability density, then we need to talk more. So, in order to find the probability density of this particular state, we can write the psi to be in terms of the column matrix like this. So if we want to talk about psi, then we can write this psi as equal to psi1 psi2 dot 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 psi-n. So this is the column matrix which is representing the state of the system. And if we want to find the corresponding probability density for the particle to be remaining, for the particle to be found in the nth state, then Pn would be equal to psi-n star psi-n, where psi-n is assumed to be a complex quantity, as we have seen for the double slit experiment. There psi was something like a to the power I et by h cross into cos of some argument which was dependent on the on the path difference. So the probability is given by this particular expression, and we can find an analogy between the vector analysis, which we have already studied. We would like to really correlate those vector analysis with this, because both are linear algebra. And we know that a norm of a vector is defined as can be defined as v is square root of v dot v. Okay, so if we want to find the norm of a vector, rather norm square, then we can write v square to be equal to v1 v2 dot 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 vn. If it is an n component vector, then a row matrix is to be multiplied with a column matrix like this, so as to find the corresponding norm square of a vector. This can be one kind of representation in terms of matrix, in terms of column matrix. And if the v is complex, for v to be complex, then we have to be little cautious, because here v dot v would be actually equal to v1 star v2 star and so on, vn star, and this should be multiplied with a column vector v1, v2 and vn, and the corresponding norm vector can be written as v1 mod square, or you can write this as v1 star v1, v2 star v2 and vn star vn. Okay, so in the same fashion we can write we can correlate this with the state of the particle, which could be the state of the electron in a double slit experiment, or the state of the particle which was oscillating to and fro in the closed pipe, as I have given in the example above. In that particular representation also one can represent the state of the system, and you have to differentiate, or you have to distinguish between the column vectors and the row vectors for complex number, and there is a notation which is called the bracket notation, Dirac bracket notation. You can always define a ket psi as equal to a column vector psi1 psi2 dot 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 psi n, and you can always define a bra vector to be equal to psi1 star psi2 star dot 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 psi n star. Okay, then one can always define the bra psi ket psi to be equal to psi1 star row vector psi2 star, the second element of the row vector psi n star, multiplied by the column vector psi1 psi2 psi3 and psi n. Okay, so this is going to give us psi1 star psi1 plus psi2 star psi2 plus dot 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 psi n star psi n, which is basically equal to the probability density of the first state, probability density of the second, and so on, Pn, which is basically equal to the total probability of finding the particle. And this, according to the statistical interpretation of, or the Born interpretation of the wave function, must be equal to unity. Now the same wave function norm can be written in the integral form also, and we call such product as self product, and one can define this psi bra psi ket to be equal to psi star psi, and if it is a one-dimensional one, dx from 0 to L, or from minus, if L be the length of the tube which we were considering, this should be equal to 1. So basically one can say that this function is a normalized function. We can represent the same integral in the same bracket notation in the form of an integral. Now if you have different function, then also one can take the scalar product like that we have taken over here. Suppose we have two different function, for example bra f ket g, then that can be written as f star x gx dx, and if they are orthogonal to each other, then this should be equal to 0. If fx is orthogonal to gx, this is similar to vector algebra, only thing is we have written it in in integral form. These two properties are called orthonormal properties of the function, which represent the quantum mechanical state of the system, and the whole thing which we learn from this is the constituent for the basic postulate number 1 of quantum mechanics. So we can conclude from this that the postulate 1 of quantum mechanics, which actually defines the representation of state, representation of quantum state, of the quantum mechanical state, is represented by a function psi x, which actually contains all the information about the system. And if one wants to perform any kind of measurement, then this psi will contain the total information about the system. Now if we want to study the postulate, if we want to go into the postulate 2, then we first of all need to understand what is meant by Hermitian operators, because this is a mathematical requirement for going to the concept of observables. Now what is an Hermitian operator? We have already studied in our previous course what can be a Hermitian matrix or an Hermitian. Any matrix which contains in general complex elements, then you can always take a complex conjugate of that particular matrix, and if the matrix is again the same as the original one, then we call that as Hermitian matrix. Here also we can define a Hermitian operator like this. Suppose I have a particular operator A, which is basically a linear operator, and I want to define a particular function. A is an operator, mathematical operator, and if I want to define a particular function like this, psi star a cap psi dx, and if this can be written as a star psi star, if I call this as psi m and this represents psi n in general, then this a star psi m star, okay, and psi n dx, then this operator is called Hermitian operator. Now we can also express this in terms of in terms of the bracket algebra. Suppose we have psi m e psi n, and so here psi m actually represent the psi m actually represents, so this is the definition of Hermitian operator. I think now it is visible quite clearly. Okay, so if we want to express the Hermitian, this is the integral representation of an operator to be Hermitian. Now if we want to represent in bracket algebra, then we can always invert this, and we can, this is basically going to give us, the left hand side is given by this, and if we want to write it like this, then this is basically a psi m, okay, and psi n. So if this is the case, the same operator can be, this is actually a dagger in general. If you just do an inversion, then this should be a, but if a operator is equal to a dagger, which is basically in terms of matrix is the Hermitian conjugate, self Hermitian conjugate, then we call such operators as Hermitian operator. Now why are we so interested in Hermitian operators? Because these are the operators, these are the linear operators which correspond to physically observable quantities, and they give us real eigenvalues. Whenever an operator operates on a wave function psi, then it gives us a particular eigenvalue. For example, if this is A operating on psi n, then it gives us an psi n, and if A operates on psi m, then it gives am psi m. So if this be the equation, then the operator actually gives us the eigenvalues an for the wave function psi n and am for the wave function psi m. So we can have an eigenvalue equation even in quantum mechanics. This psi n contains the information about the state of the system, and this operator corresponds to physically observable quantity. Any physical quantity can be represented by a Hermitian operator, and that is basically the postulate number 2. So every physical observable, postulate number 2 actually says that every physically observable quantity, observable corresponds to a Hermitian operator. Okay, so why Hermitian operator? Because these have the property to give us real eigenvalues, and they also, if they are they have some eigenfunction psi n or psi m, then we can say that psi m and psi n would be mutually orthogonal if they have different eigenvalues. So these are the two properties which we can prove very easily, and they had been proven previously also. We can prove it again here. Suppose this is not so difficult, but we let us first of all try to confirm, or let us first of all try to understand that there are few basic postulates of quantum mechanics which needs to be understood. The first one is, one can represent the quantum mechanical state by psi x. The second one is that every physically observable quantity corresponds to certain kind of Hermitian operators. These Hermitian operators are those operators which obey a particular mathematical relation like this, and they actually provide us with real eigenvalues, and they also, if they correspond to different eigenvalue for different eigenfunctions, then those eigenfunctions would be orthogonal to each other. We can prove that. Let us try to prove these two things separately.